Assalamu alaikum. Welcome to my channel Learn with Fun by Zarasar. Today we'll be discussing about a very important topic which is MOSFET. So we are continuing with our course of VLSI and nanoelectronics to complete to understand how this fabrication and the further things goes on. So let's continue. So today's discussion will be based on MOSFET, and you guys are aware about MOSFET contain two words, that is MOS and FET, where MOS means metal oxide semiconductor and FET stands for field effect transistor. So MOSFET stands for basically metal oxide semiconductor field effect transistor. And with this MOSFET we can design any circuits, either it be digital or analog. So let's start with our today's lecture. And you are aware about family of transistor. So family of transistor includes, this is a very short and sweet summarize of family of transistor, that we have BJT and FET, where BJT is as classified as NPN and PNP, while FET is further classified as JFET and MOSFET. So talking about FET, why do we move from BJT to FET is a topic that I have already taught you in your previous semester. Now for this course, you should understand that FET are of two types, junction field and MOSFET. Our target in this course is metal oxide semiconductor field effect transistor, which include two types, depletion and enhancement. Depletion is further divided as N channel, P channel, while enhancement is divided on same as N channel and P channel. So how to understand metal oxide semiconductor field effect transistor? Look at this image that you can easily visualize that our metal oxide semiconductor field effect transistor, that is MOSFET, contain a gate, a source and a drain. So this is my source terminal, this is my gate and drain. So you need to be aware about that your MOSFET contain three terminals. So that is, it is three terminal device. Actually it is called as four terminal. I'll explain why do we call sometime it as a four terminal device. Usually it is a three terminal device which contain drain, gate and source. Okay, so let's move forward and understand how we can easily understand the concept of MOSFET. So let's go to next slide and understand detail about MOSFET. So this is the real pictorial view of understanding MOSFET in detail. Okay, so let me explain you. This device which is shown on your screen is a MOSFET, which consists of a gate terminal, a source terminal and a drain terminal. So gate, source and drain. Now as you are aware about, or you have seen my previous videos of previous semesters, that gate, source and drain, these are the three terminals of a MOSFET. Let me teach you some a little bit previous concept that we need for this course. So if I'm talking about this MOSFET, it is nothing but your NMOS. So you have PMOS and NMOS that we'll be discussing, don't worry about it. This is NMOS. How do you know it is NMOS? So this is P substrate and N diffusion, we call it as NMOS. So when we apply positive voltage at gate terminal, since there are maximum positive charge and very less number of electron, the electron will get attracted toward this terminal. I mean to say gate. Okay. So if the electron get attracted towards gate, they will create a channel at the gate. So there will be a channel at the gate. So when this channel is created at the gate, the electron will flow. Now the current will flow from source to drain or drain to source. So this is the basic fundamental of MOSFET. So you should be aware about that MOSFET is a voltage control device. Okay, MOSFET is a voltage control device. So MOSFET is a voltage control device. What does this mean? That due to this gate voltage we can control the current. while BJT is a current control device. So do remember, it is nothing but current control device. Which is current control device? BJT. And MOSFET, BJT, and MOSFET is a voltage control device. So this, using this gate voltage, we can control the current. Now let's move further and understand what are the important parameters that we can assure ourselves that this thing we should keep in mind while fabricating or designing any devices. So I'll jot down some parameter that you should be focusing on. So the first parameter that you must be targeting is your channel length. So channel length is the first parameter you should be targeting. And where is channel length? This is the channel length that you need to be understand. See guys, this is the length what I'm talking about. But you can see there are two lengths which I have shown over here. One is effective length and another is length drawn. So effective length will be considering while we are trying to ignore the channel length modulation and that means when we want a precise value of drain current, we'll consider channel effective length. But if we are considering a normal MOSFET, we'll consider this L. So channel length is denoted by L, which is a very important parameter. The another parameter is channel width. So where is channel width? See, these two parameters are very important. They are known as aspect ratio. So where is channel width? See, if this is the channel length, which clearly gives me an idea, if this is the channel length, then this part will be my channel width. So this is part where I called it as my channel width. So the total width of channel length, I mean the channel created, is known as channel width. So this is my channel width. Okay. Now this becomes my channel width and this is my channel length. Now the another parameter that you should be remember or aware about it, voltages. So there are some voltages that you should be aware about. One is threshold voltage, one is gate to source voltage, and another is drain to source voltage. So these are the three important voltages that you should be aware about. Another is oxide layer, or this one, oxide capacitance. So this is the important area where you should be targeting yourself. So this area is your oxide capacitance area, okay, which is denoted usually with yellow color. Okay, so this will be COX, oxide capacitance, which is important, and COX is nothing but EOX upon TOX, which is permittivity, and this is thickness. It comes from C equal to epsilon A by D. This is the basic equation of capacitor. So you should be aware about four parameters which is important. One is channel length, channel width, voltage, and oxide capacitance. Let's move further to drain current equation. Now these are the parameters when you need to understand while understanding any MOSFET. Okay, so these are the very important parameter. Let's move further to understand the drain current equation. Okay, so let's talk about drain current equation. As you can see, the diagram on your right hand side represents the device that we have already talked about. And you are aware about from previous semester courses that there are three regions of operation. One is active, one is cutoff, and another is saturation. So just I want you to make sure that your device works in three regions: saturation, active, and cutoff. And you must be aware about that in saturation and cutoff, that act as switch generally, and for active region it acts as amplifier. Okay, so these are the two applications of switch or a device that you are aware about. So let's begin our discussion with drain current equation. So I'll be talking about cutoff current equation first because it's very simple and easy to remember. So drain current of cutoff region ID is equal to 0 since there is no current passing from drain to source. Now for active region, the equation will be talking about the four parameters that we have already discussed in our previous slide, which is channel length, channel width, voltages, and oxide capacitance. So see, you can see this equation. Oxide capacitance W by L, VGS minus VTH VDS. So there are width, length, oxide capacitance, VGS, VTH and VDS. If you want, you can simplify this equation like this: mu n Cux W by L, and if I take this 2 outside, then what will happen inside will be 2 times VGS minus VTH into VDS minus VDS square. If I take this 2 common outside, this is the 2 that I have taken common outside. Not common, I have taken it out. The reason why I have done this is, you will be surprised to know that for saturation the equation is, see, you can see this term is common, mu n Cux W by L upon 2. So this term is common over here, and you only get VGS minus VTH the whole square. So this is the equation for saturation. If you want, you can understand or simplify or memorize this, or you can solve this and get this equation for drain current using the reference book Razavi. And finally, when you reach over here, I can give you the shortcut for this. If you considered VDS is equal to VGS minus VTH in this equation, then you'll get this equation. Okay, so just need to substitute VDS as VGS minus VTH. So you'll get 2 times VGS minus VTH the whole square minus VGS minus VTH the whole square. So 2x square minus x square becomes x square. So you'll get this equation. So this is the equation for saturation. So there are the 3 equations: ID equal to 0 for cutoff, for active it is mu n Cux upon 2 W by L 2 times VGS minus VTH into VDS minus VDS square. For saturation it is mu n Cux W by L VGS minus VTH the whole square. Now let's move further and understand a fantastic things about MOSFET. So if I talk about device, we have already discussed that your MOSFET are divided into 2 types, NMOS and PMOS. Okay, but there's one more which is called as CMOS, and we are not aware about it. So just need to give you some pictorial view about NMOS, PMOS and CMOS. I want you to see these 3 pics. For NMOS, you should be aware about that in NMOS we take the substrate as P and the diffusion are N. Okay, the diffusion are N and the substrate is P, which implies the channel will be created of N. The channel will be created of N, and we called it as NMOS. So if the channel is created of N, we call it as NMOS or N-channel MOSFET. And in PMOS, the channel will be created of P-type material. So we call it as PMOS. So do remember, for NMOS, the diffusion is N, and for PMOS, the diffusion is P. So if this is NMOS, the diffusion is N over here, and if it is PMOS, the diffusion is P. Now, there are the symbols for NMOS and PMOS. So let's look at analog symbol that are used. These are the 2 analog symbols that are used for understanding NMOS and PMOS, or making circuits using NMOS and PMOS. Now, for digital circuit, to understand or to design digital circuit, we use some different symbol. You can use this symbol too, but if you go to some reference book, you will find different symbol for different notation. So this can be used to represent NMOS and PMOS in analog. The arrow over here represent an important point that current is flowing away. So that is, it is flowing from source to drain, and here from drain to source. Okay. Now this is a symbol of NMOS and PMOS in analog. This is the symbol for digital. So in digital there is no arrow, but do remember, for PMOS we have something called as bubble and the PMOS, which means it is operating as opposite of NMOS, which we can understand easily. Now let's move further. See, we will be discussing CMOS in our next lecture, which is very important and very intuitive, that we should be targeting. So if you are aware about this 3 symbol, I mean this 4 symbol, 2 for analog and 2 for digital, for NMOS and PMOS, we can move further to some fabrication type of NMOS and PMOS that we will be requiring in our practical simulation. So you can get this image and memorize it, that how it is, or you can see this image. So let's see how this fabrication can be made. And for this, let's take this example. Not example, this is the device actually. So this is the way how device looks. It contains drain, gate and source, which we have already discussed about. So let me show you that if this is my gate terminal, this is my this is my drain, gate and source. Now in this three terminal, if we see, there are something called as green color and yellow color and red color. So this color plays an important role while we will simulating this in our device or in any software. So see, this device, red color, this is a metal. Okay, this is my oxide layer and this is my semiconductor. So do remember, the yellow color always represents it is p-type material. The green color represents it is n-type material, and the red denotes polysilicon, which is gate or metal. Okay, so this yellow, it is p-type substrate. This is my n plus diffusion. Now we are aware about, if this is my n plus diffusion, it is nothing but my NMOS. So the diagram which I have drawn over here, or you can look, is NMOS. So this is your NMOS. Now this is my NMOS. Let me draw, or let me show you its top view. So the top view for this diagram is, we'll get gate, drain and source. Now gate, drain and source, as the notation or the color is red, green. So I remember it, when polysilicon layer cuts diffusion layer, a transistor is formed. When polysilicon layer cuts diffusion, transistor is formed. Similarly, for PMOS, what will be the changes? The changes just will be in the color, which means in the doping or diffusion concentration. So, see, this is the diagram for PMOS. The yellow color and NMOS becomes green color. So this become my N substrate. This is my P plus diffusion. This is my P plus diffusion. Okay. This is my gate terminal, source and drain. Gate, source and drain. Exactly same as my NMOS. Now, it also has its top view. So top view will be exactly similar to it. So we'll be having a gate, we'll be having a drain and source. Now, you should be aware that in NMOS and PMOS, the gate is red color, but in NMOS, the drain and source are represented by green color, while in PMOS, it is represented by yellow colors. So, while I am simulating this too, in software, you should be aware about the colors. Now guys, the important point is this, what I have shown, the gate of your NMOS or PMOS. Now, which are the important parameter that we have already discussed and which will be requiring in our operational amplifier design is channel width and channel length. So this is channel width and channel length. You can see this is channel width and this is channel length. Now guys, if this is my width and this is my length of channel, that means I need to be aware about W by L aspect ratio while designing. Now you can see I have written something called as 1 over here and 0 over here, which is very important. This is nothing but logic. So here it is 1 logic and here it is 0. Logic 1 means if I give positive voltage at gate of NMOS, my NMOS will get activated and current will flow from drain to source. So it's a very simple concept that NMOS will get activated when it gets 1. So NMOS will be getting activated when it gets 1. Similarly, PMOS will be getting activated when it gets 0. So you should be aware about that my NMOS and PMOS, if we move into digital world, in digital, my NMOS will be working for logic 1 and PMOS will be working for logic 0. So while simulating, I'll show you how it works and what are the problems related to NMOS and PMOS which will be solved by CMOS. So this is the part from my side. Hope you have enjoyed today's lecture. I have given you a lot of detail about MOSFET. If you have any doubts or any query, should comment below. Thank you. Have a nice day. Stay home, stay safe.